Hello, everybody. Welcome back. Today we're going to be looking at Unit 7.2, which is called The Direction of Reversible Reactions. So let's get started. All right, so let's just review for a second. Remember that we said that most chemical reactions are reversible, and we can talk about the forward direction, we can talk about the reverse direction, and the definition of equilibrium is when the speed, the rate of the forward direction and of the reverse direction are equal. So the question that this subunit poses is, well, what if they're not equal? Okay, so for example, let's say at the time where this arrow is pointing, and I'll even draw it a little better on here. So at this time, okay, whatever that time is on the x-axis, you can see that the rates in the forward and reverse direction are not equal. The rate of the forward direction, if you look at it where it falls on the y-axis, is greater than where the reverse reaction is falling. So at this point in time where the arrow is pointing, the forward reaction is faster than the reverse reaction. And what we say is, in this case, the forward reaction is favored. That's the terminology. Okay, so they will, at certain points in time not be equal, but then eventually the reactions, the different directions will, quote, settle down and they will become equal and equilibrium will be established. So let's look at a sample problem here. All right, we have a very simple decomposition reaction. AB is decomposing into A and B separately, okay, and they're being represented with these colored dots. And it says a reversible reaction is represented by the equation above. You can also see that because see how there's a double-headed arrow in the reaction. That means it's a reversible reaction. The amount of reactants and products at time 1 and time 2 are shown. Based on the diagram, what can we infer about the rates of the forward and reverse reactions over time? And we've seen these particle diagrams a lot where they represent reactants and products with dots. And so what we want to do, as we do whenever we have these particle diagrams, is count the particles. And I'm just going to focus in on the pink dot A. And I'm going to count them. At time 1, I see 1, 2, 3, 4. I'm not going to count that one because it is joined to B, so that's AB. All right, I was just counting the number of individual A particles. So I see 4 particles at time 1, whereas at time 2, I only see 2 of them. Okay, well, A is one of my products, and between time 1 and 2, I can see that this product is decreasing. Okay, there's less of it. And by the way, I didn't have to choose letter A. I could have chosen to look at how many blue particles there are, or I could have chosen how many AB particles there are. You count one of them, it doesn't matter. I just focused on A. The fact that from time 1 to time 2, there are fewer particles of A tells me that this reaction is being favored in the reverse direction because particles of A are being consumed. There's less of them. And please notice, if you were counting the number of AB molecules, in time 1, there's only 1 of them, but at time 2, there's 3 of them. So we're making more AB. So right off the bat, before I've even read the answer choices, I know that the reverse reaction is favored. So right away, I can eliminate answer choice A because it says the forward reaction is favored. I know that's wrong. Answer choice B says over time the reverse reaction is favored. Sounds good because the concentration of A decreases. Okay, that sounds pretty good, but let's keep reading. C says over time the system reaches equilibrium because the total number of A and B atoms does not change. Well, the number of A particles and B particles did change. We have no way of knowing if this has reached equilibrium, so I'm going to eliminate answer choice C. Over time, this is answer choice D, the system reaches equilibrium because the reaction stops. We know that's definitely not true because reactions don't ever stop, really. Okay, so answer choice B is my answer. All right, so this is just a way to visually represent the reaction has not yet reached equilibrium or what is happening between one time period and another time period. So that was a pretty quick one. I hope you learned a little something about looking at the direction that is being favored at a particular point in time. And I look forward to seeing you next time.